Just need to make sure it's responding. So guys, this is the deal. Today, reaction mechanisms. So you know that I've been sort of doing my best to create awareness in you of what this is going to look like on the AP test, right? And we already know what is the first question. When you get to the rate problem, and 90% of the time there's a rate problem in free response. Guys, when you get to that question, what's the first thing they're going to ask you to do? Rate expressions. And you're all going to get it wrong. And then when you're after that, what's the next thing they're going to do? They are going to feed you reaction data, and they are going to ask you to do what? Establish, and actually they separate this. Typically, they will then have you establish reaction orders. It'll say something like what are the reaction orders for these reactants. You'll go through the logic or the math, right? You can do math. You can do the logic or the math of establishing the exponents that are the reaction orders. Then typically part C is write the rate law. But you're not done. Guys, what is part D going to say? I forgot. Actually, it would. Typically, then they'll ask you to solve for K or establish the units for K. And then, guys, the part after that, and sometimes they don't have you mess around with K. A lot of times they do. But then, guys, following that, the next question that they will ask you, and this is the point of the unit, they will do this. They will say, there is the possibility that this reaction, the one you're studying, it'll say there is the possibility that this reaction happens through the following mechanism. And then they will ask you this question. Is this mechanism valid? Let me say that again. So guys, the last question in the rate question on the test will be, this reaction appears to happen through, or could happen through this mechanism. Is the mechanism valid? That's what we're going to do today, is you are going to learn to determine the validity of a mechanism. Now guys, notice this important difference. They are not asking you to propose a mechanism. And really quickly, guys, what is a mechanism? The series of steps that the reaction goes through to get from reactants to products. So guys, they will never ask you to propose a mechanism. They will ask you to validate a mechanism. Do you understand the difference? So you're never going to have to sit down and go, there's the possibility that this reaction happens through this series of steps. All you've got to do is say, here's the series of steps. Is it possible? So guys, how do you validate mechanisms? It's a two-step process, and that's what you're going to learn to do today. You guys good? Okay, so guys, with all of that as background, let's dig into this. You're going to love this. There's lots to write down, and let's get going. So guys, again, summarizing, don't write this down. Here's our goal today. Guys, our goal today is to simply develop a system for verifying mechanisms. This system, and don't write this down, this is what we're doing today. Guys, this verification system is a two-step process. Step number one, you will be asking yourself this question. Do the elementary steps, and you're going, oh crap, I forgot what elementary steps are. We'll remind ourselves in a second. Do the elementary steps add up to the overall reaction? And then guys, importantly, step two is this. Is the rate law for the rate determining step, and that's important, right? Because it's underlined. We'll talk, don't write, we'll talk. Guys, the second test is this. Is the rate law for the rate determining step the same as the rate law for the overall reaction? So guys, we already know what rate laws are, right? Rate is equal to K times concentrations raised to orders. Well guys, so here's what we need to do. To figure out this process, we need to dig into elementary steps a little more deeply, and then we need to talk about rate determining steps, and then we'll be ready to put this two-step process to the test and verify, not propose, but verify a mechanism. You guys ready to go? Go ahead.
If there are multiple elementaries
There will be.
So then would all of those rates add up to give you the total?
No, and that's, you'll see. That will not be the case. But I'll show you what will be the case. But fundamentally, as you're trying to picture this in your head, Matt, mechanisms will always be made up of multiple elementary steps. Okay, so guys, let's remind ourselves of this as we're moving forward. What does elementary mean? Not simple. What does it mean? Can't be simplified, right? Can't be simplified. Okay, so guys, here's the scoop then. And remember when we jogged through all this stuff at the end of the last class period, and I told you don't write it down because we will eventually? That's now. So guys, in order to understand all of this, you've got to understand what elementary steps are, and you guys love to take notes, so let's take some notes. So guys, it goes like this. Elementary steps are simple one-step reaction processes that only depend on the concentration of the reactants. That is the definition of an elementary step. Where do you remember this from? Who said that? Someone just said, I remember this. From where? I was hoping that you were remembering this from summarizing the chapter, and I was going to say something significant about the importance of doing chapter summaries.
Oh, I do remember seeing it, yeah.
Well, of course you do. Which is why we do chapter summary. What?
Going under the bridge. What, the cars? I don't know.
Oh, I got even something better than cars under a bridge. Yeah? What format did you use? You just outlined it. Yeah, good for you. Cool. Yeah. So guys, let's then take this to the next step. The sum of these elementary steps is then what we call a mechanism. So what is a mechanism? A mechanism is the complete picture. How does a reaction get from reactants to products in a stepwise fashion? And those steps we call elementary steps, and they are the simple, one-step, concentration-dependent reactions that take place as reactants turn into products. Now guys, these elementary steps we describe by the number of particles that act as reactants. And you may remember we have unimolecular, bimolecular, and termolecular steps. Do you guys ever notice how sometimes I just throw a bunch of stuff up on the board? You guys know why I do that, right? No, because it buys me some time to run around and gather up the stuff that I need. If I ever need more time in class, all I have to do is get you guys to write stuff. Exactly. Which doesn't start with 4 score. No. I know. Just because I don't live on 2nd floor doesn't mean I don't know anything.
Why didn't you have to take it? So you just kind of assumed citizenship.
Okay, guys, y'all caught up? Y'all caught up? Josh, focus, right. Unimolecular, bimolecular, termolecular. And Gwen, this is about to get to the thing that you and I sort of talked about. It wasn't what you were talking about, but it was what it made me think of. I don't know. I don't know. Okay, so guys, are we okay? Can we talk? Unis 1. Can you just write down Unis 1, Bi is 2, and Tur is 3? Okay, here's the deal, guys. And understand, well, let's back up. So guys, check this out. In order for a reaction to happen, what does there have to be? Collisions. So here we go. Unimolecular, okay? One particle. How can a unimolecular reaction take place if there's nothing for it to collide with? It either decomposes or it reorganizes. So guys, some unimolecular processes are decompositions. Other unimolecular processes are molecules where the atoms shift position within the molecule. That's unimolecular. Now guys, what does bimolecular look like? Hold that. And Isabel, I'm going to call you up to active duty in a second. Okay, so guys, bimolecular looks like this. For a bimolecular process to happen, we just, come on, help me. Meet me in the middle. We just need, not bad, right? I know, Matt's doing good.
Impeccable hand.
See, right. So guys, a bimolecular process simply requires two things to collide. And when they collide, assuming that they collide in proper orientation, because some collisions, we'll talk more later, some collisions don't work. Because if they don't collide hitting the proper surfaces, they won't react. That's what catalysts do, but we'll talk more later. So guys, the idea here is that so long as they collide, we're going to have a reaction. That's bimolecular. Now guys, we're going to, and remember, this happens, these collisions are random, right? This is just random movement. We are moderately intelligent, purposeful beings, and we're going to try for a termolecular process. 1, 2, 3.
I knew she was going to drop that. I should have called it.
Okay, I'm ready this time.
Okay, here we go. 1, 2. No, that wasn't quite it. 1, 2. Oh, crap. Okay, 1, 2. Oh, that wasn't. You get the idea. And that's the problem. Guys, in order for a termolecular process to happen, all three of them have got to collide at exactly the same moment. If two hit first and then another one comes in, that is not going to be an effective collision. They all have to hit not just simultaneously, but with the proper orientations that cause the reaction to happen. What are the chances of that? Bordering on 0. Right, and that's exactly, especially when we're doing, but you're right. If we've got moles of particles and high enough velocities, on average, there are going to be some effective termolecular steps, but they're not likely. So guys, in order of speed, if you've got a unimolecular process, that thing can happen all day. Things can fall apart, things can reorganize. Bimolecular steps, they also happen really quick because you just got to get two things to hit. Termolecular steps tend to be very slow. You're right, on the order of moles of things eventually are going to hit just right 3 at a time, but it's not as likely. What about tetra? What about a tetramolecular step? Yeah, guys, here's the deal. When you become a rate dynamicist in college, and I have no idea why on earth you would want to do that, but if you become a rate dynamics chemist, as you now start to propose mechanisms for reactions, there's a rule in rate dynamics that says steer away from termolecular steps. If you're comparing two different mechanisms and one of them requires a tetramolecular step, it's probably not going to happen because that's so unlikely. 4 things is almost 0 chance. 3 is pushing it. So guys, termolecular, oh gosh, what happened? Oh, Skyward crashed. Guys, termolecular steps occur very, very infrequently. And anything more than 3 is pushing no chance at all. Yeah. Exactly. So let's say that better though, Brandon. A termolecular would tend to be a slow elementary step, which would then probably lead to a slow reaction. Because guess what you're going to find out? Reactions, this is important, reactions can only go as fast as their slowest elementary step. Okay, go ahead. Mm-hmm. I have no idea, but I know that it doesn't connect right now, so I see where your brain is going, and I'd love to talk later, but it's not pertinent to what we're doing. So guys, you good with this idea of molecularity and the likelihood of these things happening? Okay, so guys, with that said then, there's another term that you need to know, and it's this. You know what, I want to underline this. So this is going to be important to us as we get into this. It's the idea of what are called intermediates. Guys, when we start talking about these mechanisms, what you're going to see is that many times one elementary step, that's not even a thing. One elementary step will create a product that then immediately gets consumed in the next elementary step. You can probably understand then why they call them intermediates, the in the middles. So guys, the idea is these intermediates are substances that are formed by one elementary step and then consumed by the next. And as a result, they don't show up in the balanced equations.
Is this like the story with the basis of like real chemistry?
No, none of this is real chemistry. You don't get, chemistry doesn't get real until you get to P-Chem your junior year. Then things get real. You guys good? Okay. So, guys, what we're going to do now is we're going to wrap our arms around some of the interplay, some of the details that we need to really grasp in order to pull this idea of mechanisms together with rate laws. So we're going to reach backwards into rate laws for a second and then bring rate laws forward and then put all of this together. So, and guys, that shouldn't be surprising to you, right? Because what was the second check for verifying a mechanism? The rate law of the rate determining step. We don't know what that is yet. But the rate law of the rate determining step has got to be the same as the rate law for the overall reaction. So let's remind ourselves about some important things about rate laws. Can you guys all sign off on this idea? We cannot write rate laws for chemical reactions from balanced equations. The coefficients in the balanced equation are not the reaction orders, right? Okay, so guys, if that's true, what do we need in order to write rate laws? We need reaction data. Trial 1, trial 2, trial 3, establish the relationships. So guys, we've got to have reaction data. Why is this true? Because the balanced equation just tells us before and after. It doesn't tell us how before gets to after. You guys all settled on that idea? Because this is going to be concerning to you if you're sold on this idea. Ready? Oh yeah, here it comes, Brandon. You're going to be okay. Catherine, be ready for him. He might faint. Guys, guess what? We can write rate laws, right? We can write rate laws for elementary steps from the balanced equations. And you guys know where this is headed. The question is why. But if you want to draw the line in the sand, because nothing's changed. We can't write rate laws for balanced equations without reaction data. But we can write rate laws for elementary steps by simply taking the coefficients from the elementary steps and making them the reaction orders. Because, of course, the question is why. So the coefficients for the balanced equations are the exponents. They are the reaction orders for the balanced equations. And, of course, the question is why. So, guys, let me let you catch up because it's really important you understand why. The thing that was really cool, though, is when this first bullet point came up where it said we can write the rate laws for elementary steps, some of you, without even knowing it, started to explain why. That's cool. You guys are pretty smart.
It's just like that dog experience.
It's funny, my wife and I were just talking about that the other day. Pavlov's dog.
Yeah.
Yeah.
The office one.
It's funny because we were actually talking about my dog. And you guys know I have the world's stupidest dog, right? But she's a lab, and she's a sweetheart. She just has no social skills. And it's funny because my dog, her name is Dakota, she actually trained us. So we don't have a dog door, so if my dog wants out, my dog has to let us know that she wants out. And so what she'll do is she'll come and she taps on the back door with her paw. We didn't teach her that. She taught us that. And if you start to think about that, I can't imagine that that's a behavior that they exhibit when they used to be wild animals. Like, something in Dakota's little dog brain went, I want to go out and I need to tell people, and I'm going to do this. And that's where Pavlov comes in. That basically, my dog trained me through what's called operant conditioning to come open the door when she taps on it.
My cat does this.
Yeah, it's fascinating. I wonder if, sorry, I can't say this in public schools, but I wonder if when we get to heaven, if we don't find out that our dogs actually speak English and they just can't talk back. I'm fairly certain they understand way more than we know.
But I shift my color.
I hope that's true.
Blink if you can understand me.
Matt, that's a side of you I didn't even need to know about. Yeah, I think it's sort of a C.S. Lewis Reepicheep kind of thing. I think they've been sworn to silence. I think you sign like a little dog like non-disclosure agreement. Yeah, right. Yeah, I will not let this secret out. All right, let's keep going. So, okay, so guys, why? This is, as Mr. Ellingford would say, important. So, guys, you've got to understand this. Why is this true? Why is it that we cannot write rate laws for overall reactions from the balanced equation, but we can for elementary steps? What is it about elementary steps that allows us to write balanced equations or write rate laws right from the balanced equations? And, guys, the answer is elementary steps have nothing to hide, right? Elementary steps, by definition, cannot be simplified. Chemical reactions, overall reactions, have all sorts of stuff going on behind the scenes. You don't know how reactants turn into products. And as a result, you can't relate concentration to rate, a rate law. You can't relate concentration to rate because you don't know what the reaction is doing with those concentrations that would affect the rate. But in an elementary step, what you see is literally what you get. How do elementary steps happen? Simple concentration-dependent collisions. If you've got unimolecular, it breaks apart. If you've got bimolecular, they run into each other. If you've got termolecular, they run into each other. There's nothing hidden. It's all just collisions. And as a result, the balanced coefficients from the equations are the exponents for the rate law because there's nothing going on behind the scenes. Does that make sense? So guys, what we're going to say then is this. The rate law for an elementary step is based directly on its molecularity. Why? Because the rate of the reaction is dependent upon simple collision concentration-dependent collisions. There's nothing going on behind the scenes. What you see is what you get. End of story. The unimolecular, bimolecular, termolecular. Oh, yeah. To know thine own self. So guys, there's one more thing that we need to do, assuming that you're comfortable with what you're now writing down. We now know that we cannot write rate laws for overall reactions without data because there's lots going on in the background. We now know that reaction mechanisms are made up of elementary steps. Elementary steps cannot be simplified. They're elementary. As a result, we can write the rate laws for elementary steps simply based upon the balanced equations, because what you see is what you get. Nothing going on in the background, and as a result, you can write rate laws right from the balanced equations. Yeah.
So can we not use the rate laws of the elementary steps to find the total rate law?
And that's what we're doing. It's not that, it's even more simple than what you just said. But that's the purpose for today, is the big idea is how can we understand things about the rate laws for the elementary steps and use that to talk about the rate law for the overall reaction. And you're going to see that there's a relationship, but to understand the relationship, there's one more concept you need to understand. You guys caught up? You okay? You guys okay? Daniel, you good? Okay, so guys, the last thing that we need to talk about is this. You'll notice I'm throwing I'm throwing a bunch of stuff up on the board. Why am I doing that? So I can get stuff done. So guys, the last thing that you need to understand is this concept of what is called a rate determining step. So guys, 4 reactions that occur in multiple steps, multiple elementary steps. The overall reaction cannot go faster than the slowest elementary step. And guys, that slowest elementary step has a name. It is what is called the rate determining step. And guys, then by definition, no surprise, the rate determining step is called that because it's the one that determines the overall rate of the reaction. What? That's okay.
Oh yeah, that awkward moment. Or when you no, like so, you know when you have your homework in your backpack and you slide a book in and it crushes it, not too hard, and then you know that you
Yeah, Matt, you're a master of organization. You keep believing that. Not at, too. Wrong preposition. Okay, not yet. All right. Ethan, do you have a cell phone? Grab it. And do you, Sam or Daniel, do you guys have a cell phone? Okay, grab it and turn on your stopwatch. Just one of you. Actually, you know what? Maybe not, Sam. It could be too far. Daniel, do you have one? Okay, turn on your stopwatch. Negative. Okay, guys. Rate determining steps. So guys, rate determining steps go like this. So here's what we're going to do. We are going to carry out a reaction that simply takes pieces of paper, we're going to call these easterly pieces of paper, and turns them into westerly recycled pieces of paper. So this is actually a reaction that simply goes from E to W, east to west. So the reactants are east, the products are west. Now, this reaction actually takes place through a two-step mechanism. Step number one, who's got the phone? You? Okay. So step number one goes Z to I. That would be Zach to Isabel. Then, guys, step number two goes from Isabel to who's got the phone? You're a pretty good shot. You're out. To Sam. Okay? Then, actually, it's a three-step mechanism. From Zach to Isabel, Isabel to Sam, and Sam to products. Don't miss. Okay, now, here's the deal, guys. The way that this works is, I need a phone. So guys, these steps don't happen at the same speed. So it turns out that for this reaction, step number one actually happens at a rate twice step number two. Okay, so the way that this is going to go is step number one happens every 10 seconds. But step number two, actually, let's change that. Step number one happens every 5 seconds. Step number two happens every 10 seconds. So guys, the way that this is going to happen, and we're going to make this a little easier on Isabella, her head would explode. So every 5 seconds, I am going to huck a ball to Ethan. Ethan is going to catch it and set it down in front of Isabel. Then every 10 seconds, Isabel is going to throw a ball to Sam, and Sam will immediately then throw it in the box. No, because Ethan's going to be calling time to you. He'll tell you every 10 seconds. You get the idea? So every 5 seconds, every 10 seconds, and then guys, as soon as Sam catches the ball, it's going in the bucket. You can't possibly have a question, so here we go. No, it's not. Just watch. This is fun. Okay, here we go. I know it does. What?
What am I counting off every 10 seconds?
Oh, you know what? We don't actually need you to time. We'll just let Sam's process be instantaneous.
So I start once I get the first.
Right, so you'll catch the first ball, you'll set it down for Isabel, but I'm throwing you another one in just a sec, in 5 seconds. And then every 10, oh, you know what? Let's do this. Gwen, he can't catch and watch this. Every 10 seconds, you're going to tell Isabel, throw. Okay, so we're going to start at the same time. 1, 2, 3, start. 2, 3, 4, 5, 1, 7, 8, 9, 10. 1, 2, 3, 4, 5, 7, 8, 9, 10. Oh, how are you guys doing down there? 3, 4, 5, 6, 7, 8, 9, 10. Oh, you missed. Okay, but guys, if we were to continue to do this, where's the bottleneck? Right here. So what's happening right here in front of Isabel and Ethan? Stuff's piling up, right? Exactly. See, guys, we've identified the rate determining step because stuff is piling up right here. I'm throwing things rapidly. Stuff is piling up here because we're getting a collection of stuff. But then when it got down here to Sam, what happened? Boom, right in the pile, right? And so, guys, here then is the question. If you were looking at this from the outside and all you could see is me throwing a ball and that ball magically going in the bucket, how fast do the balls get in the bucket? Every 10 seconds, right? Overall, that ball goes in the bucket every 10 seconds because that's all the faster Sam is receiving balls and Sam's ditching those. So really what Sam should have done would have been more like the no-touch pass, right? It should have come and he should have just tapped it in here rather than catching it and rethrowing it. But guys, you see the connection, right? Overall, balls go from here to here every 10 seconds. You don't know that I'm throwing these every 5. All that you know is they're going in the bucket every 10. That's the difference between an overall reaction and a mechanism. The overall reaction is just balls from here to there. And if that's all we know, it just happens every 10 seconds. But if you could look at the mechanism through which one goes to the other, you start to see the complexity and you understand that this is the bottleneck. And the overall process only goes as fast as the bottleneck. You get it? Guys, that's what a rate determining step is. Yeah. So the whole reaction is the sum of the processes. Okay? Correct. That's exactly. So the overall reaction is just point A and point B, beginning and end. The mechanism are the steps that happen along the way that the balanced equation don't even represent. Yeah. No, so the individual steps are the elementary steps. And then those all together are the mechanism which give us the before and after. Is that okay? Go ahead.
So you add the time it takes to each of the steps, and that's your overall.
No, because this happened every 5 seconds, this happened every 10 seconds, this happened instantaneously. But how often did the balls get in there? It wasn't every 15 seconds, it was every 10.
What's the first one? Oh, I see.
Do you see what I'm saying? So the overall reaction, it's amazing this stupid throw balls around the room does such a good job of modeling this. The overall reaction doesn't take the sum of the elementary steps. It simply relies upon the speed of the slowest step.
But what if there was one after that that took a certain amount of time also?
Is it faster or slower?
Even if it wasn't what you have to at that time?
No, not at it. But if so, imagine, and that's what I was trying to set up previously, and I was going to slow Sam down a little bit, but then I decided that might be distracting. But imagine if Sam only threw a ball every 30 seconds. Then they're going to pile up here, right? So it doesn't matter how fast or slow these go. Sam's going to sit on these for 30 seconds, and the overall process would be 30 seconds. Exactly, right. So the overall reaction is determined by the rate determining step. Just a second, go ahead, Matt. No, we're going, Matt. He was waiting. Go ahead.
So I have two questions. The first is, wouldn't it take 15 seconds from the first to the beginning of the reaction?
No.
Right away.
Yeah, right.
But
Right.
like in a chemical reaction, if it like this bell is dependent on an intermediate substance, doesn't it take time for the intermediate substance to
But even if it took time, if it took less time than the rate of that, and understand that this is where we're getting into, because we're really talking about molarities and collisions and constant, and anyway, but if it took, regardless of the time that it took, if it's less than that overall time, then it's not going to slow the reaction down.
So even if you, like if you waited 15 seconds, waited 5 seconds,
Okay.
and handed it to Isabel.
But that's just changing our 0 point. Because by definition, the reaction starts when something happens. And it's not like we can stand here and go, okay, the reaction's starting. Oh, and by the way, here's a ball, right? Because the reactions, it doesn't matter what we say, it starts when we throw a ball. Right, yeah.
And then my other question is, if actually no, it's basically
You okay?
yeah.
Okay, so go ahead.
And then let's say Sam took 5 seconds, it would just skew it like later or whatever.
Right.
Yeah, that's what I was saying.
Right, exactly. You guys get the idea? Not bad, right? Okay, so now guys, look at where we're at. We now know some important things. We understand molecularity, uni, bi, ter, so on. We also understand that elementary steps together make up the mechanism. And these elementary steps can't be simplified. Consequently, we can write rate laws right from the balanced elementary steps. And now, guys, we understand that the overall speed of a reaction is simply going to be the same as the slowest elementary step, which we call the rate determining step. Can I get an amen? All right, so guys, what we're going to do now then is we are going to take this backwards, and this is question, what did we decide, E or F or whatever it is on the AP test. It's going to be verify the mechanism. And guys, again in review, to verify a mechanism, two things have got to be true. The elementary steps have got to add up to the overall reaction, and two, the rate law, and notice this means something to you now. The rate law for the rate determining elementary step has got to be the same as the rate law for the overall reaction. Why is that true? Because a reaction can only go as fast as its slowest step. So let's put this to the test. Guys, don't write down the sentence, but I will have you write down the rest. So this is what the question might look like on the AP test. The reaction between nitrogen dioxide and carbon monoxide, as represented below, is suggested to take place through the following two-step mechanism. Verify the mechanism is valid. It doesn't mean it's right, it just means it's possible. And this is what they'll give you first. They'll give you the mechanism, and they'll give you the overall reaction. Write this down with me. And space it out as I have. So guys, that first reaction is simply what's described in the sentence. Nitrogen dioxide, carbon monoxide, forming nitric oxide, NO, and carbon dioxide. That's the reaction. We're going to call it the subject reaction. Then guys, down below that, we have this possible two-step mechanism. And we're going to verify it. I don't know why this keeps happening to us. We may end up working into the bell for a second. Is that okay? Okay. I love that we have this freedom. Freedom. You guys good? You caught up with me? Okay, so guys, again, this is the way they're going to shell this out for you on the AP test. They're going to give you a subject reaction. Then they're going to give you a mechanism to verify. This is the way that you do this. Do this with me. So guys, to verify this mechanism, step number one in verifying the mechanism is add them together. So here's what you're going to do. Bring all of your reactants down. So what I like to do is this. I like to draw an arrow, keeping my columns lined up, and then bring all of your reactants down. So we've got NO2 and NO2. Those are the reactants in the step one. And then NO3 and CO. Those are our reactants in the second step. Then we've got NO3, NO, NO2, and CO2. So guys, now I've brought down the products from both reactions. So now guys, let's cancel. Anything that cancels. So I've got an NO2 here and an NO2 there. I've got an NO3 here and an NO3 there, and I think that's all I can do. But now look at what we've got. NO2, CO, NO, CO2. Look familiar? We just passed test number one. We now know that the elementary steps add up to the overall reaction. Guys, please, on the AP test, don't forget this step. You're going to get to this question on the test, and you're going to get so excited because, oh, look, I wrote rate laws, and I got, oh, and then you're going to forget to do this simple check where you make sure they all add up, and this is going to be the test that invalidates the mechanism, and you're going to get the question wrong because you forget to do this. So, guys, make sure they add up first. And now we know that they do. So we can now say that the elementary steps add up to the overall reaction, and that argues for the mechanism being valid. You okay? By the way, guys, let's do this really quickly. What's NO3? Good. It's not charged. It's nitrogen trioxide, but that's not even my question. Guys, what is NO3? It's an intermediate. It is created by one elementary. I love how earnest you were. Nitrate. Now it is. I know, see? So guys, notice that NO3 is created here, and it is consumed there, and it is not in the balanced equation. That's an intermediate. Okay? You don't even know it's there. You don't even, from looking at the balanced equation, you would never know that nitrate is being, now I'm doing the Brandon thing, that NO3, you would never know that this is being created and consumed because it's happening behind the scenes. It doesn't go in, it doesn't come out. It's an intermediate. Is that okay? Okay. Now, guys, we've talked about step number 1. Now we need to talk about step number 2. Verification step number 2. Verification step number 2 says this: the rate law for the overall reaction is the same as the rate law for the rate determining step. And guys, in order to make that comparison, we need to know the rate law for the overall reaction. We need to know the rate law for this. Guys, do not write this down. Why can't I do that? Yeah, you can't determine the rate law for a balanced equation from the balanced equation. What do you need? You need rate data. So guys, that's the next thing that they will give you in this question is rate data. Now we can figure out the reaction orders. So how, and can we just work through? We got 4 more minutes. So guys, how can we do this? Remember what we're going to do. We're going to reference trials and establish controls. So guys, referencing trial 1 and 2, where NO2 is controlled and the concentration of CO doubles, what happens to the rate? Doesn't change. Making NO2 a 0 order reactant. CO a 0 order reactant. Then referencing trials 1 and 3, where CO is our control and the concentration of NO2, and we can even write this down, this doubles and the rate goes up by a factor of 4, making NO2 a 2nd order reactant. Is that okay? So now we can write the rate law. So guys, write the rate law for the overall reaction in your notes. So guys, here's what we now know. The rate law for this reaction is rate is equal to K. Which one was 2nd order? NO2? Good? That's the rate law for the overall reaction. Now guys, bring your mental attention, if you will. Bring your mental attention back to the second check. And we're going to step back for a second. Check number 1. Do the elementary steps add up to the overall reaction? Yes, we've already verified that. That was this work, right? We know that the elementary steps add up to the overall reaction. Now what we've got to do is we've got to do check number 2. To do that, guys, what we need is the rate for the overall reaction. You know what? I'm going to write this on the other side, I think. Yeah, we're going to write this over here. So this overall reaction is rate is equal, is that right? Yeah. Okay, so that's the rate law for the overall reaction. But remember the test. If this mechanism is valid, just like with our paper balls, if this mechanism is valid, then the rate law for the rate determining step will be the same as the rate law for the overall reaction. So, what do we need to do? Well, we need to write the rate laws for the elementary steps. But guys, check out what we can do. Do this with me. Rate is equal to NO2. Sorry, I'm sort of out of space, but you get the idea. NO2 times NO2. Sorry, and a K. And then guys, down here, rate is equal to K times NO3 times CO. Hey. We have student recognition? Do we get treats? Did the teachers that gave him these grades get treats? All right. Hi, Joel. Hey, just grab a seat. So, guys, let's finish the thought. Let me throw this at you. This isn't the case, but just in case this becomes the case. Guys, what if there was a 2 there? What if there's a 2? Then it becomes the exponent, okay? Is that okay? Okay, so guys, with that said, now look at what we've got. We've got the rate law for the overall reaction. We've got the rate law for the elementary steps. And remember where these came from. The rate law for the overall reaction, rate data. The rate laws for the elementary steps, just from the balanced equations. So now let's remind ourselves of the second test. It says this: the rate law, if the mechanism is valid, the rate law for the rate determining step will be the same as the rate law for the overall reaction. What do we now need to know? Which one is slowest? And they will tell you. Guys, quite literally, they will just write it off to the side and they'll say fast and slow. Seriously. So now here's what we know. This is our slow step. That is our rate determining step. So did we pass test number 2? We did. Because what is NO2 times NO2? NO2 squared, which is the same as this. So the rate law for the rate determining step is the same as the rate law for the overall reaction. We just passed both tests, and this mechanism is valid. Guys, understand this though, Austin, don't miss this. Understand, guys, this doesn't mean it's right. It just means it's possible. That's what actually makes being a rate dynamicist so hard and interesting, is just because it's possible doesn't mean it's right. And as a result, guys, you actually spend a lot of time trying to figure out if your mechanisms are right. One of the ways that you do that is by trying to isolate intermediates. Because if you can find NO3 being produced in any concentration during this reaction, there's a better possibility that that intermediate is actually, that elementary step is what's doing that. So anyway, so guys, how then would you say this in total? Well, this is what you would do. You would do this. Test number 1. You would do this. Test number 2, which also, of course, requires that reaction data. And then when this is all said and done, you would simply say, this mechanism is valid because the elementary steps add up to the overall reaction, and the rate law for the rate determining step is the same as the rate law for the overall reaction. You get the idea? All right. So guys, let me give you your homework. This is going to be a little out of left field. It's this. Guys, here's the deal. I'll keep recording. Here's the deal. The book, our book does a really nice job of providing opportunities for you to fiddle with these ideas through homework. Not in this case. Just straight up, the end of chapter questions relative to this are not great. So what I'm going to do is I frankly thought I was going to have time to do this first period and just didn't. While you guys are working in lab today, I'm going to run down to the copy center and I'm going to run you copies of questions out of a Princeton review book that we are going to use as additional practice with these. So you will do these 69 through whatever. But then guys, we're also going to do these questions, and while you're working, I'll have copies for you before the end of the day. You guys need a break? Okay, we'll see you in a few.
Wait, what about the grade thing?
The what?